Good evening, and welcome to The Sleepy Scientist. I hope you're somewhere comfortable, perhaps lying back, lights dimmed, ready to let your mind drift like a cloud at sunset. Tonight we're floating into one of nature's most familiar mysteries, the secret life of clouds. Those quiet travelers above us that paint the sky, shape the weather, and, whether we realize it or not, help make life on Earth possible. Before we get started, I'd love to know where you're watching from. Is it cloudy where you are right now, or maybe a clear starry night? It's always fascinating to see where in the world these calm journeys reach. If this video helps you relax, or if you simply enjoy exploring science at a slower pace, please consider giving it a like and subscribing to The Sleepy Scientist. To those who have already joined this gentle corner of the internet, thank you. And if you haven't already, you can tap the notification bell so you won't miss the next time we drift off into another quiet story from the universe. Now, I do hope this video doesn't end up being too interesting that it keeps you awake, but if it does, at least you'll drift off knowing a little more about how the sky breathes. So what exactly is a cloud, and how does something so weightless manage to hold up millions of tons of water in the air? A cloud is one of nature's most delicate illusions, an enormous structure made of the tiniest things imaginable. Each one is a congregation of countless microscopic droplets or ice crystals, all floating together in a delicate balance between gravity and air. What we see as soft and fluffy is really a complex dance of temperature, motion, and moisture. To understand clouds, we have to start with the invisible world of water vapor, the unseen breath of the planet. Warm air can hold more vapor than cold, and as air rises and cools, it reaches a moment of transformation, the dew point. Here, invisible vapor becomes visible droplets, forming the first faint threads of cloud. In that instant, the sky turns from transparent to tangible. Every wisp you see marks a place where the atmosphere has changed its mind, where heat has turned to coolness, where air has released what it was holding. Clouds are, in a way, the Earth's gentle exhalations. They're more than decoration. They regulate the planet's temperature, reflect sunlight back into space, trap heat below, and return water to the surface as rain or snow. Without them, our world would swing wildly between freezing nights and scorching days. With them, the climate softens, the planet breathes evenly. But despite their beauty and importance, clouds are still one of the great puzzles of modern science. Satellites circle the Earth, computers model their behavior, and yet no single equation perfectly captures their complexity. They shift and shimmer, never staying still long enough to be entirely understood. In this quiet journey, we'll drift through the many faces of clouds, how they are born, how they live, and how they fade away. We'll wander from the tiny salt grains that start them, to the thunderheads that tower over continents, and the wispy cirrus clouds that drift higher than any bird can fly. Along the way, we'll see how these floating gardens of vapor shape weather, influence climate, and fill our skies with endless stories. So take a deep breath and let your thoughts slow down. The world outside is still turning, the clouds above are still moving, and together we're about to discover how something so soft can hold the power to change the earth below. High above the ground, where the air begins to cool and thin, a quiet transformation unfolds, one so gentle it usually goes unnoticed. The story of every cloud begins not with thunder or lightning, but with a single invisible breath of vapor, deciding it has cooled enough to reveal itself. This is the moment when the unseen becomes seen, when air turns visible and the sky paints its first soft brush stroke. To understand this delicate threshold, imagine the air as a sponge. Warm air, like a dry sponge, can hold a great deal of water vapor, tiny invisible molecules bouncing freely between oxygen and nitrogen. As the air cools, that sponge shrinks. It can no longer hold the same amount of moisture, and what it can't carry condenses into droplets. That magical turning point is called the dew point, the temperature at which vapour begins to condense into liquid water. This is where clouds are born. But the air doesn't simply decide to cool, something has to lift it. When air rises, it expands because the pressure around it decreases. Expansion takes energy, and energy is taken from the air's internal warmth. As a result, the air cools as it climbs. This is known as adiabatic cooling. Think of it as the atmosphere's version of decompressing after a long day. It stretches, relaxes, and chills out. There are many ways this lifting happens. Sometimes the sun gently warms the ground, and pockets of air begin to rise in lazy spirals, thermal updrafts that form those cottony fair-weather clouds. Other times, mountains force air upward, wringing out moisture as mist on their slopes. Along fronts, warm air is pushed over heavier cold air, forming sheets of layered clouds stretching for hundreds of kilometres. Even a city skyline or a forest canopy can nudge air upward enough to make a faint haze appear. Once the air reaches its dew point, something remarkable happens. The water vapour doesn't just turn into droplets out of nowhere, it needs tiny surfaces to cling to. These are aerosols, microscopic particles of salt, dust, or even pollen. Around each one, a droplet forms and grows. A typical cloud droplet is only around 10 micrometers across, so small that it would take about 100 of them to span the width of a human hair. In every cubic centimetre of a cloud, there might be hundreds of these droplets, all suspended together, too small to fall but large enough to scatter sunlight and appear as white mist. From a distance, the process looks effortless, a gentle puff drifting into view. But within that puff, physics is busy at work. The newly condensed droplets release tiny amounts of heat, latent heat of condensation, which slightly warms the air, helping it rise a little higher. This feedback fuels the cloud's growth, like a soft engine powered by temperature differences, and so the cloud expands upward and outward, layer upon layer, until its base marks the level where air first became saturated. You can see this threshold with your own eyes on a humid day. Watch the horizon and notice how flat the base of a cumulus cloud appears. That line across the sky is the lifting condensation level, the invisible boundary where vapour gives up invisibility. Below it, air is unsaturated and clear. Above it, the sky turns milky with suspended droplets. It's as though the atmosphere drew a perfect line and said, "Here, this is where the visible world begins." The same transformation plays out closer to the ground too. On a cool morning, your breath meets chilly air and turns into a fleeting cloud. That visible mist isn't actually steam. True steam is invisible. What you see are tiny water droplets formed when warm, moist air from your lungs cools rapidly and condenses. The same thing happens when a kettle whistles or when you see mist curling above a lake at dawn. It's water performing its favourite trick, showing up unannounced when the air gets cool enough. If you could drift through a newly formed cloud, you might expect to feel wet, but you'd hardly notice anything at all. The droplets are too small and too far apart to soak you. The air inside a cloud is actually just as dry as the air outside. Saturated, yes, but not dripping. You'd be surrounded by millions of tiny spheres, each glinting faintly with refracted sunlight, moving with the wind and colliding gently, sometimes merging into larger drops that will one day fall as rain. From a scientific perspective, the birth of a cloud is the atmosphere's way of maintaining balance. When warm, moist air rises, it redistributes heat vertically through condensation and convection. The process moves energy from the surface to higher levels, fueling weather systems and sustaining the global circulation of air. Every cloud you see, no matter how small, is part of that invisible machinery keeping Earth's climate stable. And yet, for something so common, clouds remain deeply personal. They shape the light of our days and the moods of our skies. They're the difference between a washed-out noon and a golden sunset. A passing cloud can dim the sun just enough for you to notice the warmth fade from your skin or make a rainbow appear in the distance. In their simplest form, clouds are condensed vapor, but in their quiet way, they're also emotion, reflection, and memory suspended in air. Perhaps that's why people have always seen more than physics in them. Poets see imagination, farmers see forecasts, children see animals and ships, and scientists looking closer see the precise interplay of thermodynamics and motion that makes all of it possible. Every cloud, no matter how ordinary, began with a simple moment of cooling, a parcel of air rising, expanding, and reaching the point where it could no longer stay invisible. It's a reminder that even the most delicate wonders start from change. Warm breath meeting cool night air, vapor turning to mist. The world showing us that sometimes, to become visible, all you need to do is let go of a little heat. Every cloud begins with a gathering of companions, not just droplets of water, but something even smaller, tiny specks floating invisibly in the air. These are aerosols, the quiet architects of clouds, without which the sky would remain forever clear. Each droplet needs a starting point, a little surface to cling to, something solid or soluble to make condensation possible. Without these microscopic seeds, even the most humid air could cool below its dew point and still refuse to form a single visible wisp. It might seem strange that something as pure-looking as a white cloud depends on particles of dust, smoke, or salt. But that's the paradox of the atmosphere. Its clarity is built on its impurities. These airborne specks, known as cloud condensation nuclei, or CCN for short, provide the scaffolding upon which water vapor condenses. In a way, every droplet is an extrovert. It prefers to gather around a tiny friend. Many of these particles come from the sea. When waves crash and bubbles burst, they fling microscopic grains of sea salt into the air. These salt crystals are hygroscopic, meaning they love water. Even in slightly humid air, they begin to absorb moisture and swell, forming perfect seeds for droplets to grow upon. The ocean, endlessly breathing and breaking, is one of the largest factories of cloud seeds on Earth. But not all CCN are born from the sea. The desert contributes too, sending plumes of mineral dust high into the atmosphere. Each grain may travel thousands of kilometers, crossing oceans to seed clouds on entirely different continents. The Great Sahara, for instance, regularly sends fine sand westward across the Atlantic, where it helps birth clouds over the Caribbean and South America. That same dust carries nutrients like iron and phosphorus, feeding the Amazon rainforest below. A delicate airborne bridge between continents. Volcanoes, forest fires, and even living trees join this unseen collaboration. Wildfire smoke injects soot and organic particles into the atmosphere, creating potent CCN that can spread for hundreds of kilometers. Some trees release volatile compounds that react in sunlight to form new aerosols, tiny droplets of organic haze that reflect sunlight and contribute to cloud formation. In this sense, the biosphere and the atmosphere are intertwined. Forests not only breathe out oxygen, but also whisper seeds for clouds into the sky above them. And then there's human activity, factories, vehicles, ships, all sending out their own cloud seeds. Pollution adds large numbers of fine particles to the air, often much smaller than natural dust or salt grains. When air rich in these particles begins to rise and cool, it forms an abundance of droplets. So many, in fact, that they end up competing for the available water vapor. This results in clouds made of many tiny droplets, giving them a brighter, more reflective appearance. Clean air, by contrast, tends to produce fewer condensation nuclei, meaning fewer but larger droplets, which can grow more easily into raindrops. It's one reason polluted regions often have hazy, long-lived clouds that rarely rain, while cleaner regions can see those same clouds release showers more readily. The presence or absence of aerosols also influences how clouds interact with sunlight. Tiny droplets scatter light more efficiently, giving clouds their characteristic white brilliance. Larger droplets allow more sunlight to penetrate, often giving clouds a slightly darker, greyer tone. It's subtle, but the play of light in the sky above is shaped as much by microscopic particles as by weather systems or winds. Some of these particles can do something even more remarkable. They can help ice form in clouds that are still warmer than freezing. These are called ice nucleating particles, or INP. Certain types of mineral dust, ash, and even bacteria have molecular surfaces that encourage water molecules to arrange themselves into ice crystals. Without them, water can remain liquid well below 0 degrees Celsius in a state known as supercooling. Many clouds, especially those high in the atmosphere, are filled with droplets that are technically colder than ice yet still liquid, waiting for just the right kind of particle to trigger freezing. When one droplet finally freezes, it can start a chain reaction. Ice crystals grow rapidly by collecting vapor from nearby supercooled droplets, and as they fall, they may melt into raindrops or remain as snowflakes. The entire weather we experience on the ground, rain, hail, snow, can trace its origins to these silent interactions between water and dust high above. It's a humbling reminder that storms can begin with something smaller than a speck of pollen. The sources of these nucleating particles are astonishingly diverse. Microscopic fragments of clay lifted from dry lake beds, salt blown from distant shores, the faint residue of cosmic dust entering the atmosphere, all can serve as seeds for ice. Some of the most efficient INPS come from biological sources. Tiny fragments of leaf litter or bacteria, such as Pseudomonas syringae, contain special proteins that mimic the structure of ice, helping water molecules lock into place. These biological agents can ride air currents for days, influencing the weather thousands of kilometers from their origin. It's almost poetic, life helping to make the very rain that sustains it. The Earth's ecosystems are engaged in a quiet feedback loop with the atmosphere, each breath of wind carrying the ingredients for renewal. The number and type of aerosols in the air can change rapidly depending on the region and season. Over remote oceans, the atmosphere may contain only a few dozen condensation nuclei per cubic centimetre. Over busy cities, that number can rise to tens of thousands. The effects ripple outward. More particles mean smaller droplets, which can suppress rainfall and keep clouds alive longer. Fewer particles mean larger droplets, more rainfall, and shorter-lived clouds. In the long run, this balance affects not only local weather, but also the planet's energy budget, how much sunlight is reflected or trapped. Imagine standing by the sea on a windy day, the air thick with salt spray. Each invisible grain that escapes a breaking wave might one day rise into the sky, joining with others to weave a cloud. Far away, another cloud might begin from a puff of desert dust or a trace of smoke from a distant fire. Together, these countless particles link ocean, land, and air in a continuous conversation. For something so minute, aerosols have immense influence. They govern whether a cloud will be bright or dim, wet or dry, fleeting or persistent. They are the silent fingerprints of every environment, recording where the air has been and what it has touched. Even in the cleanest sky, there are billions of them floating by, shaping the weather you feel on your skin and the view you see above. It's easy to forget that the softness of a cloud depends on the roughness of what it starts with. A tiny grain of salt, a bit of soil, or the smoke from a fire. In that way, the sky is democratic. Every particle, no matter how humble, can become the center of something vast and beautiful. So the next time you see a cloud drifting lazily overhead, remember that it began as a whisper of dust, a breath of ocean, a flicker of life. The heavens, it turns out, are built from small talk, billions of invisible seeds, each one quietly convincing water to gather round and shine. If clouds are the art of the sky, then rising air is the brushstroke that paints them. Every wisp, puff, and towering column begins with air that refuses to stay put. It drifts upward, expanding and cooling as it climbs, sculpting the atmosphere into patterns of motion and light. The way that air lifts, gently or dramatically in broad layers or narrow columns, decides whether the day will bring tranquil skies or towering storms. At the heart of it all lies a simple truth. Hot air really does rise. No debate club needed. When sunlight warms the ground, it also warms the air resting just above it. That air becomes lighter, less dense, and begins to ascend through the cooler layers above. But the atmosphere isn't uniform, it's arranged in delicate, ever-shifting layers, each with its own temperature and humidity. Whether a parcel of air keeps climbing or sinks back down depends on how quickly those layers cool with height, a rule known as the lapse rate. The environmental lapse rate describes how the surrounding air temperature changes as you go upward. On average, it cools by about 6.5 degrees Celsius per kilometre, though this changes constantly depending on the time of day and local weather. Meanwhile, a rising parcel of air cools according to its own adiabatic lapse rate, about 10 degrees Celsius per kilometre when the air is dry, and about 5 or 6 degrees when it's saturated with moisture. The reason moist air cools more slowly is that condensation releases heat, giving the air a small boost as it rises. If the atmosphere cools faster than the rising air, the parcel stays warmer and lighter than its surroundings, so it keeps floating upward. The air is said to be unstable, and clouds will grow tall and full of life. But if the atmosphere cools more slowly, the parcel quickly becomes heavier and sinks back down. The air is stable, and clouds that form will stay flat and spread out like a thin sheet. That's why some days the sky looks like an even layer of pancakes, while others erupt with towers that stretch toward the stratosphere. One of the gentlest and most beautiful examples of lifting comes from thermals, rising columns of air born from uneven heating at the surface. Fields, lakes, and forests all absorb sunlight differently. A dark ploughed field warms quickly, while nearby water stays cool. The warmer patch becomes a launch pad for a bubble of air that rises slowly, expanding as it goes. Birds often take advantage of these invisible elevators. Hawks and vultures spiral effortlessly within thermals, climbing on nothing more than sunlight and physics. You can sometimes see thermals made visible by clouds. A fair weather cumulus often marks the top of a thermal, where the air has cooled just enough to reach its dew point. Beneath that cloud, invisible currents breathe upward and fade away, giving life to the soft shapes above. If the air aloft is stable, those clouds remain small and flat-topped. But if the atmosphere is unstable, one cloud may rise higher than the rest, billowing and stretching as if sculpted by slow motion. Beyond these gentle updrafts, the atmosphere has other ways of forcing air upward. Along fronts, where warm and cold air masses meet, the lighter warm air slides up and over the denser cold air, forming long, smooth sheets of layered clouds that can stretch across entire countries. When air meets mountains, it has no choice but to climb, cooling and condensing into orographic clouds. These clouds often wring moisture from the air, releasing rain or snow on the windward side while leaving the leeward slopes dry and clear. Many of the world's deserts exist because of this pattern, a rain shadow cast by mountains that intercept the sky's moisture. Even large-scale pressure systems can create lift. When air converges near the surface, it has nowhere to go but upward. Higher up, air spreads out to make room, creating vast regions of slow, steady ascent. These are the hidden engines inside low-pressure systems, the swirling cores that generate most of our weather. Whether in the gentle rise of a warm front or the towering thrust of a thunderstorm, the same rule applies. Air that rises will cool, and cooling air will often make clouds. The strength of that upward motion determines the character of the clouds that form. Meteorologists measure this potential as convective available potential energy, or CAPE. It's a way of describing how much buoyant energy a parcel of air has to rise. High CAPE means the air is primed for dramatic convection. Tall, powerful clouds and the possibility of storms. Low CAPE means gentle, lazy skies, where clouds form quietly and dissolve without fanfare. Most days fall somewhere in between, with the atmosphere humming along in slow equilibrium. But the sky is rarely perfect in its balance. Even strong updrafts must contend with entrainment, the mixing of dry surrounding air into the rising column. This intrusion of dryness cools and weakens the air, stealing its buoyancy and sometimes eroding the cloud from within. That's why the edges of clouds often appear soft and frayed, slowly fading into blue. The atmosphere, it seems, never lets a rising parcel have the last word. From the ground, these invisible forces appear as endless variety. On some days, sunlight sparks small cotton-like clouds that hover over fields until dusk. On others, a single thermal may grow into a great column, rising until it touches the boundary between weather and space. The same physical laws shape them all. Only the strength of the lift and the layering of the air decide how far they will go. Even within one cloud, 100 tiny battles unfold at once. Warm pockets surge upward, cool regions sink back down, and the boundary between them ripples like the surface of a slow-moving sea. When you see a cloud's edge bubbling and reshaping itself, you're watching those hidden currents in action, the pulse of a living sky, breathing in warmth and exhaling mist. There's something quietly poetic about how the air behaves. The same sun that warms your face also sets invisible rivers flowing above your head, building towers of vapour from simple warmth. Thunderstorms, for all their grandeur, begin as whispers of rising air, born from the same physics that lifts a child's kite or carries the scent of rain. Every cloud is a conversation between heat and gravity, between motion and stillness. The air lifts, it cools, it meets resistance, and it learns where to stop. The result is a sky always in flux, an ever-changing mural of balance and breath. And as you look up and see those drifting forms, remember, the sky above you is not still. It's rising, falling, and reshaping itself every second, quietly learning the ancient art of lifting the world. For something that seems endlessly changeable, the sky actually follows a quiet order. Every shape of cloud, from a paper-thin veil to a towering anvil, belongs to a great atmospheric family. They are categorized not by whim or poetry, but by how high they live and how they move. Learning their names is like learning the language of the air, a way to read the mood of the sky at a glance. The modern naming system dates back to the early 19th century, when a British pharmacist and amateur meteorologist named Luke Howard decided that the heavens deserved some organisation. Instead of fluffy thing number 2 or the one that looks like a horse, he used Latin, because of course, everything sounds more elegant in Latin. His simple but brilliant idea was to classify clouds by both their form and their altitude. Those Latin roots have survived ever since, turning everyday weather into something that feels almost classical. At the broadest level, there are 3 main forms: cumulus, stratus, and cirrus. The fourth, nimbus, is a modifier used when a cloud is producing rain or snow. The forms describe appearance and behaviour, whether a cloud heaps, spreads, or threads across the sky. while their altitude bands define their homes, low, middle, or high. Add a few prefixes and suffixes, and you have the entire atmospheric family tree. Low-level clouds usually live from the surface up to around 2 kilometers high. These include stratus, stratocumulus, and the lower forms of cumulus. Stratus are the blanket clouds, flat grey layers that cover the sky like a comforter pulled tight. They often bring drizzle, or at least the feeling that drizzle might start at any moment. Stratus clouds form when moist air rises gently over cooler air, creating uniform sheets instead of bubbling towers. Stratocumulus, their more textured cousins, have a bit more personality. They appear as lumpy grey rolls or patches that may stretch from horizon to horizon, often breaking apart to reveal slivers of blue. They mark the transition between calm and convective skies, neither fully stable nor wildly unstable. They're the compromise clouds, happy to just hover without too much drama. Cumulus are the crowd pleasers. These are the puffy, bright white heaps that children draw instinctively when they imagine the sky. They form from rising thermals of warm air that condense into soft cotton shapes. On most days they stay modest, scattered across the sky. Their flat bases all neatly aligned at the same altitude, the lifting condensation level. But given enough heat and moisture, cumulus can grow upward into cumulus congestus, or even cumulonimbus, the towering thunderclouds that dominate entire skylines. Mid-level clouds found between about 2 and 6 kilometers up include altostratus and altocumulus. Altostratus clouds are thin, greyish veils that often dim the sun without completely hiding it. They signal a change in weather, often appearing ahead of warm fronts that will later bring rain. Altocumulus are small, patchy formations that can look like fish scales or fleecy roes, sometimes called a mackerel sky. These clouds often form from gentle waves of air rippling through the middle atmosphere, and their presence tells you that moisture and instability are quietly increasing. Higher still, in the cold and rarefied air above 6 kilometers, are the cirrus clouds. These are the wisps, streaks, and feathers of ice crystals that drift near the top of the troposphere. Cirrus clouds often appear before a change in weather, stretched into long filaments by strong upper winds. They can be delicate as silk, catching the last light of the day in brilliant reds and golds long after the sun has set. Because they are made of ice, their fibres sometimes scatter light into halos and sundogs, tiny rainbows that shimmer beside the sun. When these high and low forms mix, we get hybrids: cirrostratus, cirrocumulus, altostratus, altocumulus, stratocumulus. Each name is a combination of 2 Latin clues, one describing shape, the other describing height. Cirrostratus, for instance, are the thin, icy veils that can produce halos around the moon. Stratocumulus blend the layering of stratus with the puffiness of cumulus, forming quilt-like patterns that ripple gently across the lower sky. Then there are the rainmakers. Nimbus, meaning cloud or rainstorm in Latin, turns an ordinary formation into something active. Nimbostratus are thick, grey blankets that pour steady rain or snow, the kind that can linger for an entire afternoon. Cumulonimbus are the towering thunderheads, immense vertical structures that reach from low levels up to the tropopause, sometimes 15 kilometers high. Within them, air churns upward and downward at tens of meters per second, generating lightning, thunder, and hail. From the outside, they appear majestic, even peaceful, but within them lies one of nature's most powerful engines. The form of each cloud is shaped by physics, the balance between rising motion, moisture, and the stability of the air. Flat layers mean air is lifting slowly and evenly. Towers mean it's rising fast and with force. Puffy clouds form where the atmosphere encourages upward motion. Smooth ones form where it resists. Even the edges tell a story. crisp outlines reveal strong updraft and active condensation, while frayed ones hint at dry air nibbling away at the cloud's sides through entrainment. You don't need instruments to start reading the sky. With a bit of practice, you can tell whether the day is warming or cooling, whether moisture is increasing or fading, simply by watching the texture and altitude of the clouds. A line of cumulus growing taller by the hour means convection is strengthening. A spreading layer of cirrostratus around the sun means a front may be on the way. When clouds flatten out or vanish, it's a sign that the atmosphere is stabilizing. It's like reading a slow-moving diary written by air and light. On a summer afternoon, you might lie back in a field and watch the cloud family at work. Low, lazy cumulus drift by like ships on a calm sea. Higher up, thin cirrus clouds trace the paths of invisible jet streams. Occasionally a veil of altostratus slides in, softening the brightness of the sun. The entire sky is alive, each level whispering its own version of the same story, airlifting, cooling, and turning moisture into form. It's easy to see why people once looked to the heavens for signs and omens. The patterns above us are not random at all. They're the visible handwriting of the atmosphere. And though Luke Howard gave them Latin names 2 centuries ago, their beauty still needs no translation. So the next time you find yourself gazing upward, try naming what you see. Cirrus for the streaks, stratus for the blankets, cumulus for the heaps, and nimbus when the rain begins to fall. The language might sound ancient, but it's really just Earth speaking in clouds, a conversation between sunlight, air, and water that anyone with a little attention can learn to understand. Every thunderstorm begins with something small, a single cottony puff drifting above a sun-warmed field. It looks harmless, even playful, but inside that soft shape, a powerful engine is beginning to turn. Air is rising faster than you can run, moisture is condensing by the ton every second, and invisible drafts are building the foundations of a skyscraper you can't lease. The life of a cumulus cloud is a story of growth. Quiet at first, then restless, then magnificent. The earlier stage begins with the fair weather cumulus. These are the daytime dreamers of the sky, white puffy heaps floating lazily above flat bases. They form when warm air near the surface rises, expands and cools to its dew point. At first, the upward motion is gentle, the kind of lift that might carry a bird on an easy glide. Inside, droplets collide and merge, but the cloud remains shallow. If you were to watch one closely, you'd see it constantly rebuilding itself, new wisps forming on top as the lower parts fade and evaporate. It's a living structure, breathing in sunlight and breathing out vapor, but sometimes the conditions are just right for ambition. If the air above is unstable and the rising current is strong, that innocent puff keeps climbing. As it rises, the droplets within release latent heat, giving the air extra buoyancy, which helps it soar even higher. The result is a cumulus congestus, a growing tower that begins to look less like a pillow and more like a column of marble. Updrafts inside may reach speeds of 5 to 10 meters per second, enough to hurl droplets upward faster than gravity can pull them down. From the ground, it's a mesmerizing sight. The edges boil and roll as warm, moist air rushes in from below. The top blossoms and billows, glowing brilliant white against the blue. Each new burst of rising air adds another layer, like bricks laid by invisible hands. The architecture of the cloud becomes more defined, its vertical reach more daring. It's a slow-motion construction project powered by sunlight. Eventually, the tower climbs high enough to reach the freezing level, the altitude where the temperature drops below 0 degrees Celsius. Here the droplets begin to freeze into tiny ice crystals, releasing yet more heat that fuels the updrafts even further. The cloud, now tall enough to pierce multiple layers of the atmosphere, enters its next stage. Cumulus calvus, a cloud whose once rounded top begins to lose its soft outlines, turning fibrous and blurred. Calvus means bald, an oddly appropriate word for a cloud shedding its smoothness as ice takes hold. As the cloud keeps climbing, it may reach the upper limits of the troposphere, around 10 to 15 kilometers high. The air here is thin, cold and stable, forming a kind of invisible ceiling called the tropopause. When the cloud finally hits this barrier, it can no longer rise freely. Instead, it spreads outward, forming the signature flat anvil-shaped top of a mature cumulonimbus. The Latin name for this stage, capilletus, means hairy, referring to the wispy, icy filaments that drift from its crown. It is both beautiful and formidable, a monument of condensation sculpted by the laws of thermodynamics. Inside this immense structure, chaos reigns. Powerful updrafts hurl droplets and ice pellets skyward, while downdrafts drag cooler air back down toward the surface. Some regions are purely liquid, others are mixed with ice and supercooled water, droplets that remain liquid even at temperatures below freezing. When these collide, ice grows by collecting water droplets, a process called accretion. As they bounce around, fragments break off, creating smaller ice crystals that grow in turn. The result is a turbulent cascade of collisions, freezing and melting, a hidden storm within the cloud. This is where lightning begins, though not quite in the dramatic way it's often imagined. Inside the towering anvil, collisions between ice particles separate electrical charges. Lighter, positively charged crystals drift upward, while heavier, negatively charged graupel and hailstones sink downward. The growing separation builds an enormous electric field, like tension gathering in the air. When the charge difference becomes too great, the air between them breaks down and a spark leaps through the sky. Lightning is that spark on a colossal scale, heating the air to tens of thousands of degrees and causing it to expand faster than the speed of sound, the sharp clap we know as thunder. For something so violent, the process itself is the product of simple physics multiplied by scale. What begins as a warm breeze over a sunny meadow becomes a tower 15 kilometers high, carrying millions of tons of water and ice. It's powered entirely by rising air and phase changes, evaporation, condensation, freezing, melting, all happening in unison, recycling energy between invisible and visible states. The power of a thunderstorm lies not in something alien or mysterious, but in the same water cycle that softens clouds at sunrise. Even at its fiercest, the cloud remains a masterpiece of balance. The anvil top, spread wide across the sky, marks where upward momentum finally meets equilibrium. The updrafts, having spent their energy, give way to gentle descent as raindrops and ice begin to fall. The towering cumulonimbus is entering its mature stage, heavy with moisture, darkening at its base. What once was a brilliant white puff now casts a deep shadow over the land. Beneath it, the air feels charged, electric and heavy with scent, ozone and wet earth mingling before the rain begins. When the first drops fall, they've already lived an entire life inside the cloud. A raindrop begins as a tiny droplet that collided with thousands of others, growing large enough to overcome the upward pull of the wind. Each one carries a memory of its journey, frozen, thawed, and refrozen countless times as it tumbled through updrafts and downdrafts. By the time it reaches the ground, it has travelled through more vertical motion than most mountain climbers will in a lifetime. Eventually, as the rain cools the air below, the updrafts weaken. The cloud's energy runs out, its once mighty towers soften, and the anvil begins to spread and thin. The storm fades into layered remnants that drift away, leaving behind only distant rumbles and the sweet smell of rain. Within an hour or two, sunlight may break through again, and new puffs of cumulus begin to form in the warm, moist air left behind, seeds for the next generation of clouds. It's a remarkable thought that every thunderstorm, no matter how enormous, begins with a single bubble of warm air rising from the surface. From puff to power, from playfulness to grandeur, it's the same story told at different scales. Each towering cumulonimbus is a monument to sunlight and moisture, the Earth's way of releasing stored heat back into space, and of reminding us that even the gentlest forces, air, water, warmth, can together build something truly spectacular. Far out over the ocean, far from the sight of land, lies one of Earth's most important and least appreciated wonders, a vast glowing quilt of cloud that stretches to the horizon. These are the marine stratocumulus clouds, the quiet guardians of the planet's temperature. From above they appear as endless plates of white, stitched together in soft rolling patterns. From below they turn the sky into a pale ceiling, shading the waters beneath. Together they act as nature's biggest duvet. Do not attempt to fold. Despite their calm appearance, these clouds play a commanding role in the global climate. They cover about 1/5 of the Earth's surface at any given time, particularly above the cool waters of the eastern oceans, the Pacific off South America, the Atlantic off Africa, and the coasts of California and Peru. These regions are known as cold tongue zones, where upwelling ocean currents bring cold water to the surface. As warm, moist air drifts over these chilled seas, it cools from below, forming thick layers of stable air capped by a strong inversion. Within this shallow layer, a delicate balance is struck between upward mixing and the cooling sea beneath, and that balance gives birth to the marine stratocumulus deck. The inversion is the key. Normally air cools as it rises, but in these regions a warmer layer of air sits on top of cooler air near the surface. This acts like a lid, trapping moisture and turbulence below. Clouds can't rise freely through it, so they spread out sideways instead, forming vast thin sheets. It's the atmosphere's way of saying, you may grow, but only in 2 dimensions. The result is a cloud field that can stretch for thousands of kilometers, so uniform and persistent that it shows up clearly in satellite images as bright, glowing patches against the darker blue of the sea. Inside these seemingly still layers, the air is anything but motionless. Small pockets of warm air rise from the ocean surface, while cooler air sinks, creating a slow, rolling convection. Gentle overturning cells only a few hundred meters tall. The tops of these cells form the cloud layer, their bottoms the ocean surface. This quiet churning helps to mix moisture and heat, keeping the cloud alive. Occasionally, small drops of drizzle form and fall a few hundred meters before evaporating, just enough to maintain the balance without clearing the sky. It's a kind of self-regulating system, a slow heartbeat of the marine atmosphere. These clouds are masters of reflection. Their bright surfaces bounce sunlight back into space, cooling the planet beneath them. This reflectivity, known as albedo, makes marine stratocumulus one of the most powerful natural regulators of Earth's temperature. Even a small change in their coverage or brightness could alter the global energy balance. A slightly thicker deck can reflect more sunlight, cooling the ocean. A slightly thinner one can let more sunlight through, warming it. Scientists study them obsessively because they are both stable and fragile. Small shifts in wind, humidity, or pollution can make them change their mind about existing. From space, their patterns can appear mesmerizing. Some regions show closed cells, tight honeycomb-like formations of cloud, with clear air trapped inside each loop. These occur when the air near the surface is relatively moist, allowing the cloud deck to remain unbroken. Other times, as drier air intrudes or drizzle increases, the pattern flips to open cells, where holes appear between the cloud patches, like lace stretched over the ocean. This subtle difference, open or closed, can dramatically change how much sunlight is reflected or absorbed and how much heat escapes to space. It's astonishing that such thin, gentle clouds can have so much influence. Their average thickness is only a few hundred meters, but collectively they act as a planetary mirror. They cool the ocean's surface by several degrees, stabilizing the climate of the regions beneath. Ships traveling through them sometimes leave temporary holes or trails in the cloud layer, ship tracks, where emissions act as extra condensation nuclei, creating smaller droplets and changing the cloud's brightness. These narrow, linear scars are fleeting reminders of how sensitive these clouds are to their environment. Beneath the deck, the ocean remains calm and grey, its surface dappled with shifting patterns of light. The air is cool and damp with a faint scent of salt. Even the wind seems softened by the blanket above. These are quiet seas, rarely stormy, where the rhythm of the atmosphere is measured in gentle, persistent motions rather than violent bursts. Pilots flying above describe the sight as breathtaking, a glowing textured carpet stretching to infinity, with the tops of the clouds rolling and rippling like the surface of a sleeping giant. For all their beauty, marine stratocumulus clouds are also one of the great uncertainties in climate science. They exist in a fragile equilibrium between cooling and warming forces. If the planet warms too much, the inversion layers that sustain them could weaken, allowing the clouds to break apart. Without their bright reflective cover, the oceans would absorb more sunlight, warming even faster. A feedback loop that researchers are still trying to understand. Some computer models suggest that a few degrees of warming in the right places could thin these clouds dramatically, changing the entire global energy balance. It's a reminder that the planet's thermostat depends not on towering storms or sweeping winds, but on these quiet, persistent sheets of vapor drifting above the oceans. They don't flash or thunder, and they never make headlines, but they quietly decide how much sunlight stays and how much leaves. Every sunrise over the Pacific, every cool sea breeze along the California coast owes something to their unhurried work. It's tempting to think of them as passive, but they're more like the planet's caretakers, regulating, adjusting, breathing. Each patch is the product of countless tiny droplets, each droplet formed around a grain of salt flung from a breaking wave. Together, they stitch a pattern that holds steady against the turning of the world, maintaining balance one reflection at a time. So the next time you look at a satellite image or fly above the ocean and see that endless white expanse, remember the quiet miracle beneath it. Those bright clouds are not just decoration, they're an active part of the planet's heartbeat. And while they may look like nothing more than a soft ceiling over calm seas, they're in truth one of Earth's most vital defences, endlessly weaving and reweaving their silver quilt across the blue. There are some clouds that seem to ignore the rules. While most drift and shift with the wind, these ones appear to stand perfectly still, smooth, curved and luminous, hovering above mountain peaks like otherworldly ships. These are lenticular clouds, the sculpted children of mountains and motion. From the ground, they look so solid, so deliberate, that it's easy to see why they've inspired countless UFO reports. But in truth, their mystery has nothing to do with aliens, and everything to do with physics. When air flows across the landscape, it behaves like water in a stream. A mountain is simply a boulder in its path. The air is forced upward over the ridge, cools as it rises, and then sinks again on the other side, warming as it descends. If the air is stable enough, meaning it resists vertical motion, it doesn't just rise and fall once. Instead, it overshoots, then oscillates up and down in a repeating pattern, creating invisible waves that can stretch for tens or even hundreds of kilometers downstream. These are called atmospheric gravity waves, named not because they defy gravity, but because gravity acts as the restoring force that pulls the air back toward equilibrium. Where these waves lift air to its cooling point, moisture condenses into cloud. Where they sink, the air warms and the cloud evaporates. The result is a series of stationary cloud patches that appear to hang in place, even though the air within them is constantly rushing through. To an observer on the ground, it's a visual paradox. The cloud itself doesn't move, but the air that makes it never stops moving. It's like watching a river ripple over a rock. The shape is steady, though the water is always new. The classic lenticular cloud forms at the crest of the first wave, often just downwind of a mountain peak. Its smooth lens-like shape is the natural product of laminar airflow, where the air moves in clean layered sheets rather than turbulent eddies. Each layer has slightly different temperature and humidity, sculpting the cloud into a form so precise it looks man-made. Sometimes, multiple waves stack atop one another, creating a series of layered disks that seem to balance in the sky. When lit from the side by the setting sun, they glow gold, pink, and amber, silky stacks hovering at dusk, impossibly serene. From a pilot's perspective, these clouds are both beautiful and dangerous. Beneath their smooth tops, powerful updrafts and downdraft ripple through the air like unseen rapids. Glider pilots, however, see opportunity. By surfing these standing waves, skilled gliders can ride upward currents to extraordinary heights, sometimes reaching the stratosphere. Records have been set in these conditions, flights above 15 kilometers without an engine, powered only by the invisible waves born from mountain winds. The leeward side of the mountain, however, tells a different story. As air descends and warms, it often dries out completely, leading to clear skies and a sudden rise in temperature known as a foehn or chinook wind, depending on where you are in the world. These warm downslope winds can melt snow, lift dust and bring abrupt relief or discomfort to the valleys below. Residents of the Alps, the Rockies, and the Andes all have local names for them, each with its own folklore. To some, the foehn brings sleepless nights and headaches. To others, it's a welcome thaw. Either way, it's a reminder that the same air-shaping lenticular clouds above can transform life on the ground below. Sometimes, the interaction between these waves and the terrain creates far more turbulent features. Beneath the smooth lenticulars, violent rotating eddies known as rotor clouds can form. They roll along like airborne tumble dryers, spinning horizontally beneath the wave crest. To pilots, they mark a warning zone of severe turbulence, but from a safe distance, they're mesmerizing. Bands of swirling vapor tracing the hidden machinery of the wind. Even these turbulent features have their beauty, like the froth at the base of a waterfall. What makes lenticular clouds so captivating is their balance of stillness and motion. They're sculpted entirely by moving air, yet they appear frozen in place. Their stability depends on precise conditions, the right wind speed, the right temperature profile, and enough moisture to form droplets but not too much to cause rain. Shift any one of those ingredients, and the shape dissolves, the wave disappears, and the sky becomes ordinary again. It's as if nature spends hours crafting a masterpiece, only to erase it the moment it's finished. The scale of these clouds can be astonishing. A single lenticular formation may stretch across hundreds of kilometers, its smooth contours following invisible contours in the atmosphere. On some days they appear in ranks, like fleets of translucent ships stationed along the wind's path. On others, a solitary disk hovers over a single peak, glowing faintly against the blue. The sight is so precise, so symmetrical, that even seasoned meteorologists pause to admire the elegance of it all. High-speed time-lapse photography reveals their secret life. Constant renewal. Air rushes into the upwind side of the wave, condenses into cloud as it rises, and then evaporates as it sinks out the other side. The shape stays, the particles change. A perfect illustration of impermanence. It's a lesson written across the sky. Form without permanence, beauty born from motion. Lenticulars also remind us that mountains shape the weather far beyond their own borders. The waves they generate can propagate upward, influencing jet streams and even creating ripples in high cirrus layers thousands of kilometers away. These atmospheric undulations can transport energy, moisture, and momentum, subtly influencing the balance of weather systems across entire continents. What begins as air spilling over a ridge in Patagonia or the Himalayas can end up modulating the winds far above the North Atlantic. From the ground, though, they speak a simpler language, one of stillness and grace. If you ever find yourself in a mountain valley as the sun sets and the wind quiets, look up. You might see a smooth glowing disc suspended in the fading light, layered like a stack of porcelain plates. It won't move, not even as the wind rushes past, and it will vanish as silently as it appeared. For all their elegance, lenticulars are proof that even in chaos there can be symmetry. They form when the atmosphere is just restless enough to dance but calm enough to keep time. UFO reports, but make it physics. They are the sky's sculptures, ephemeral, mathematical, and endlessly mesmerizing. Etched not in stone or metal, but in air itself. High above the weather we feel and the storms we see, the sky wears a veil of ice. Thin, delicate, and often invisible until the light catches them, cirrus clouds drift near the top of the troposphere, 5 to 13 kilometers above the ground, where the air is too cold for water to remain liquid. They are the highest regular clouds on Earth, made not of droplets, but of crystals, and they are the artists of starlight, painting halos and glows around the moon with the finest brush imaginable. Cirrus clouds don't build or billow, they glide. Each one is composed of countless tiny ice crystals, some shaped like columns, others like hexagonal plates, floating gently through the thin air. They form where air rising from below cools and loses its moisture to freezing. Unlike their lower cousins, these clouds rarely bring rain or snow to the ground. Their ice crystals are too small, and they often sublimate, turn straight from solid to vapor, before they ever reach the surface. Instead, they decorate the upper sky, shaping the way sunlight and moonlight dance across it. Because of their altitude, cirrus clouds see a different world from the one we inhabit below. The air there is so dry and cold that crystals can persist for hours, carried along by strong upper winds that stretch and twist them into delicate streaks. Those streaks, combed across the dark evening sky, tell stories of jet streams and distant storms. Sometimes, cirrus form naturally from the outflow of high thunderclouds, their ice spreading out from the tops of anvils like ripples from a stone dropped in still water. Other times, they're born from jet aircraft, contrails that linger, spread, and evolve into broad sheets of cirrostratus, tracing the invisible highways of the upper atmosphere. Cirrostratus clouds are the painters behind one of the sky's most gentle miracles, halos. When the moon or sun shines through a thin layer of these icy veils, light is bent or refracted as it passes through the crystals. The geometry of each crystal, typically a hexagonal prism, deflects light by about 22 degrees, creating a glowing ring of pale colour encircling the light source. On some nights, that ring is subtle, just a faint shimmer. On others, it gleams clearly, haloing the moon like a silver crown. In ancient times, such halos were read as omens of change, but they're really just nature's way of saying, there's ice in the sky tonight. Sometimes a different pattern appears, sundogs, parhelia, or mock suns. These bright spots form when the sun's rays pass through horizontally aligned ice plates, creating twin bursts of light on either side of the sun. Though they're most visible during the day, faint versions can appear at night as moondogs, lending the darkness a kind of gentle symmetry. All of these optical effects come down to the same quiet principle: light encountering order in chaos. Each ice crystal acts as a miniature prism or mirror, bending and scattering light in predictable geometric ways. It's glitter, applied very responsibly. The variety of crystal shapes within cirrus clouds helps decide what kind of light shows appear. In the bitter cold of the upper troposphere, typically between -30 and -60 degrees Celsius, water vapour freezes into distinct habits. Columns at colder temperatures, plates at slightly warmer ones. Each shape bends light differently, producing everything from bright halos to rare arcs and pillars that seem to rise straight from the horizon. These phenomena remind us that even the simplest materials, ice and light, can weave endless variations when given enough space and time. Cirrus clouds don't just play with light, they also influence the balance of heat on Earth. Because they are thin and high, they let most sunlight pass through but trap infrared radiation emitted from the surface. In that way, they act a bit like a gauzy blanket, transparent by day, insulating by night. This dual nature makes them tricky to understand. Depending on their thickness, altitude, and crystal shape, cirrus clouds can either warm or cool the planet. They are, in a sense, the atmosphere's subtle regulators, shifting the balance with barely perceptible gestures. When viewed from the ground, cirrus may look motionless, but they're never still. Winds at their altitude can exceed 200 kilometers per hour, sculpting the clouds into fibrous streaks, curls, and hooks. These patterns even have their own poetic names: cirrus vibratus, filaments stretched thin across the blue; cirrus and sinus, delicate hooks or commas that often foretell changing weather. Their shapes reveal the hidden choreography of the jet stream, those narrow rivers of fast air that circle the globe. Where the air speeds up or slows down, moisture condenses into cirrus, tracing the sky's invisible topography. Sometimes bits of these high clouds begin to fall, forming what are known as fall streaks, thin, tapering trails of ice crystals descending from the base of the cirrus layer. They often evaporate before reaching lower altitudes, leaving behind wisps that look like celestial feathers drifting through the dusk. In certain conditions, these fall streaks can create optical illusions called hole-punch clouds, circular gaps in a cloud layer where falling ice has evaporated the air below. To those on the ground, they look like portals or fingerprints in the sky, a reminder that even the most tranquil clouds have dynamic lives. On moonlit nights, cirrus clouds can transform the heavens into a canvas of silver and shadow. The moon's light, far weaker than the sun's, still catches in the crystals, scattering across the sky and giving it a faint milky glow. Stars peek through the gaps, twinkling like distant sparks through a gauze curtain. The sight feels ancient, as though the planet itself was softly exhaling. These high clouds don't obscure the stars, they embellish them, lending the night sky depth and texture. For travellers, cirrus clouds have long served as gentle messengers. When they appear in long, thin filaments stretching across the horizon, they often signal that a change is coming, a front approaching, or moisture spreading ahead of a distant storm. They are the first whispers of weather, arriving a day or two before the real action begins. Farmers once read their shapes to predict rain. Sailors saw them as signs that the wind might soon shift. Even now, pilots watch them closely, knowing they trace the upper winds that guide their paths. To gaze at cirrus is to look at the intersection of art and physics. They are reminders that not all clouds are heavy or dark. Some exist only to decorate the light. Each filament is a record of invisible motion. Each shimmer a moment when light meets ice at exactly the right angle. They remind us that even in the coldest reaches of the sky, beauty persists. So if you find yourself walking at night under a bright full moon and notice a faint ring surrounding it, take a moment to appreciate what you're seeing. You're witnessing light bent through countless tiny crystals, each one drifting high above you, carried by winds that never rest. It's a delicate performance, silent, fleeting, and impossibly precise. The sky is glittering again, only this time applied very responsibly. Sometimes the sky decides it doesn't want to hover above us at all. It prefers to come down and pay a visit. That's what fog really is, a cloud that's misplaced its altitude. Instead of floating gracefully overhead, it settles on the ground, blurring the world into soft outlines and muted sounds. Streets disappear into white, trees fade into silhouettes, and every light seems to glow a little more kindly. It's the same physics as any cloud, just closer, quieter, and a little more personal. A cloud decided to visit. Please mind the doorstep. Fog forms when the air near the surface cools enough for its invisible water vapour to condense into tiny droplets, each one about 10 micrometers wide. The moment air reaches its dew point, the temperature at which it becomes saturated, those droplets begin to appear, turning clear air into milk. The key is temperature and moisture in perfect balance, cool enough to condense, moist enough to sustain it. Because it happens right where we live and breathe, we can watch the process unfold around us, a living science experiment that turns the familiar into something mysterious. There are several types of fog, each born from its own set of circumstances. The most common is radiation fog, which forms on calm, clear nights when heat radiates away from the ground and the air cools rapidly. As the surface loses warmth, the layer of air just above it chills to the dew point and condensation begins. This is the kind of fog that pools in valleys and fields before dawn, hugging the landscape like a blanket. When the sun rises, the fog slowly thins from below as the air warms again, retreating upward in delicate glowing sheets. Then there's advection fog, which occurs when warm moist air drifts over a cooler surface, such as when ocean air moves over cold coastal waters or snow-covered land. The contrast causes the moist air to cool quickly, condensing into thick banks that can roll inland like slow waves. This is the fog of harbours and sea cliffs, the kind that swallows lighthouses and mutes the sound of gulls. Along the Pacific coast of the Americas, advection fog is a regular summer visitor, drifting in from the ocean each afternoon and vanishing again by morning. Sailors used to call it sea smoke, though it's gentler than its name suggests. Another variety is valley fog, which gathers when cold air sinks into low-lying areas at night, trapping moisture beneath an inversion layer. The air above remains clear while the valley below fills with cloud, as though the sky had simply descended for a rest. From a mountaintop, it can look like an ocean of mist stretching between peaks, with only the highest ridges poking through like islands. Pilots flying above it call these fog seas, and they can last for days in still winter weather. It's the same principle as a pond forming in a hollow, only here the liquid is suspended in air. Even cities have their own kind of fog. When moisture condenses around the countless tiny particles of pollution and dust in urban air, it creates what meteorologists call smog, a blend of smoke and fog that thickens the haze. Though less romantic than mountain mist or sea fog, it's a powerful reminder that human activity shapes even the sky's quiet moods. Modern clean air laws have reduced smog in many places, but the phenomenon still lingers in the cold, still air of industrial valleys around the world. What makes fog so enchanting is its ability to transform the ordinary. A familiar street becomes a corridor of light and shadow, every sound dampened and distant. Footsteps echo softly. Trees fade into grey silhouettes. their branches beaded with droplets. Bridges vanish mid-span, swallowed by white, giving the illusion that they stretch into infinity. Even a simple walk feels like stepping into a dream, part science, part poetry. There's a curious comfort in fog's intimacy. Unlike most weather, which comes roaring or flashing through, fog simply arrives and settles in, rearranging the boundaries of the visible world. It hides the horizon, quiets the background, and leaves only what's near. Some find that unsettling, others find it peaceful. It's as if the world has been edited for clarity, showing only what matters for the next few steps. Of course, fog also has its practical side. It can reduce visibility to just a few meters, which is why foghorns, beacons, and careful driving exist. The same droplets that make a meadow beautiful at dawn can make a runway invisible or a coastline vanish into grey. Still, there's something reassuring in how calmly nature handles the balance. Fog rarely arrives with wind or rain. It's a stillness weather, patient and contemplative. From a scientific perspective, fog and low cloud are nearly identical. The only distinction is altitude. Fog forms when the base of a cloud touches the ground. Meteorologists measure this transition using cloud base height, which can vary from a few meters to several kilometers depending on humidity and temperature. On mountaintops or tall bridges, you can often find yourself standing inside a cloud without realizing it. One moment the air is clear, the next you're wrapped in vapor, with droplets forming on your eyelashes and clothes. The line between earth and sky, it turned out, is negotiable. Sometimes fog is fleeting, lasting only until the morning sun warms the ground. Other times, especially in coastal or winter conditions, it lingers all day, thickening and thinning in subtle rhythms. The droplets inside it aren't static. They grow, shrink, merge, and vanish with every tiny change in temperature or wind. On calm nights, you can see this happen if you shine a flashlight into the mist. Droplets glinting like dust motes in slow motion, an entire microcosm drifting through the beam. Fog's cousin, the low stratus cloud, behaves much the same way but floats slightly higher, forming a ceiling that can stretch across entire regions. Pilots describe this as a grey overcast, but from the ground it's often indistinguishable from thick fog. The two trade places constantly, fog lifting into low cloud as the day warms, cloud sinking into fog as night cools the surface. Together, they're part of the atmosphere's breathing cycle, a slow rise and fall that regulates moisture near the surface. And when fog finally begins to lift, it does so with theatrical grace. The light softens first, shifting from silver to gold as the sun breaks through. The mist thins into drifting wisps, then into translucent veils until the world reappears, familiar again but somehow renewed. Grass and leaves sparkle with dew. The air smells fresh and metallic. What was hidden is revealed, and what was ordinary seems, for a moment, miraculous. Fog reminds us that clouds are not distant things. They visit, they touch, they wander through our world. Whether rolling in from the sea, pooling in a valley, or curling through city streets, they're made of the same water that cycles endlessly through the sky and back again. The next time you wake to find the world wrapped in white, take a slow breath and listen. The sky hasn't disappeared. It's just come down to keep you company for a while. Every drop of water in the sky is a tiny prism waiting for sunlight to pass through it. Under the right conditions, those droplets turn ordinary rain into something remarkable. A burst of colour suspended in air, a bridge of light with no beginning or end. Rainbows, halos, and glories may seem like magic, but they're simply the language of light interacting with water and ice. The beauty lies not in their mystery, but in their precision. A rainbow begins with sunlight meeting a raindrop. As light enters the droplet, it slows down and bends. This is refraction. Inside, the light reflects off the back of the droplet's curved surface, then bends again as it exits. Each colour is refracted by a slightly different amount because each wavelength of light travels at a different speed through water. Red bends the least, violet the most. The result is a fan of colour emerging at a specific angle, about 42 degrees from the direction opposite the sun. That's why rainbows always appear in the part of the sky facing away from sunlight, with the centre of the bow directly opposite the sun itself. The reason you see a curved arc rather than a full circle from the ground is simply geometry. The Earth gets in the way. But from an airplane, where there's nothing to block the view, a rainbow is often a complete ring. Light scattered perfectly around the shadow of the aircraft. Every droplet in a shower contributes its own tiny piece of the rainbow. You only see the ones sending light to your eyes at just the right angle. It's a private show, uniquely yours, shifting slightly as you move. Sometimes, if conditions are right, a second, fainter bow appears outside the first. This secondary rainbow forms when light reflects twice inside the raindrop before leaving. Because of that second reflection, the colours are reversed. Red on the inside, violet on the outside, and the light is dimmer, often only visible when the sun is bright and the rain fine. Between the two arcs is a darker band known as Alexander's band, named after the ancient scholar who first described it. The darkness there isn't shadow, it's simply the region where no light from the droplets reaches your eyes. Even the gaps between colours are ruled by geometry. The spectrum of a rainbow looks smooth, but it's the result of countless individual droplets, each sending a miniature beam of coloured light in your direction. The purity of those colours depends on how uniform the droplets are. Large droplets produce bright, vivid bands, while smaller ones create pale, blended rainbows. Mist and fog with their tiny droplets often make fog bows, ghostly white arcs with faint traces of colour. They are rainbows in miniature, so soft they seem more like dreams than physics. While rainbows are born from liquid water, halos belong to ice. High in the sky, thin cirrostratus clouds scatter sunlight through billions of tiny ice crystals, each shaped like a hexagonal prism. When light enters and exits these crystals at specific angles, it bends by 22 degrees, creating a circular halo around the sun or moon. On bright days, the ring can be dazzling. At night, under a full moon, it's silvery and haunting. In ancient times, people saw halos as omens of change, and in a way they were right. They often herald the arrival of moisture and approaching weather fronts. Different crystal shapes produce different effects. Long pencil-like columns can create vertical pillars of light above the sun at sunrise or sunset, known as sun pillars. Flat plate-like crystals aligned as they fall produce sundogs, bright spots of colour to the left and right of the sun, often glowing red and blue like phantom companions. These optical phenomena are all governed by the same principle, light interacting with symmetry. The ice doesn't care where it is in the sky, it simply obeys geometry. Closer to home, there's another phenomenon more intimate and mysterious, the glory. It appears when sunlight scatters backward through the mist, forming concentric rings of colour surrounding the shadow of your head. You'll see it most often from an airplane window, where the plane's shadow rests on a cloud below, encircled by a faint rainbow-coloured halo. Hikers on misty mountains see it too, projected onto foggy slopes around their own silhouettes. A vision so personal, it once inspired legends of ghostly spirits known as Brocken spectres. The physics behind it is elegant. Light waves bend, scatter, and interfere around each droplet, reinforcing certain wavelengths and cancelling others. It's diffraction and reflection, working in harmony to create something that feels spiritual. Another member of this optical family is the corona, a delicate ring of pastel colours that surrounds the moon or sun when light diffracts through uniformly sized droplets. Unlike halos, which come from ice. Coronas form in liquid water clouds, thin layers of stratus or altercumulus. Their colours are softer and closer together, often appearing as a pearly glow rather than distinct bands. Iridescence, a related effect, shows up as random patches of pinks, greens and blues near the edges of thin clouds. These are caused by interference of light waves, tiny differences in droplet size and spacing turning the sky into a natural oil painting. Every one of these displays, rainbows, glories, halos, coronas, is a lesson in scale and precision. The sun's light travels 150 million kilometers, strikes a droplet less than a millimeter wide and still manages to find your eyes in perfect order. The geometry never falters. It's astonishing to think that something as grand as a double rainbow or as subtle as a lunar halo depends on particles so small they could fit on the head of a pin. Light doesn't discriminate, it simply reveals the structure of what it passes through. Whether refracted by raindrops, reflected by ice, or diffracted by mist, it behaves according to the same timeless laws. Yet those laws, when filtered through the fluid chaos of the atmosphere, create endless variations, each display unique, fleeting, and never to be repeated. Imagine a quiet shower at sunset, the air warm and calm. The rain begins to fade and suddenly, against the retreating clouds, a spectrum appears. Red, orange, yellow, green, blue, indigo, violet, an entire physics textbook written in colour. The air seems to glow. Or picture a cold winter night, a pale moon high above, surrounded by a perfect silver ring that makes the world feel both vast and enclosed. These are moments when science feels like serenity, when equations become art. And while you might not find a pot of gold at the end of any rainbow, what you do find is better, a glimpse into the quiet genius of light itself. Each colour, each reflection, each soft shimmer in the sky is a reminder that beauty and order are woven into the simplest things. Raindrops, ice crystals and sunlight meeting at just the right angle. Physics is the real treasure, patiently waiting to reveal itself every time moisture meets light. The sky has a routine, a quiet rhythm that plays out every day whether we notice it or not. Clouds, like so much of the atmosphere, follow a daily pattern, rising, shifting, and fading in time with the sun. You might think of it as the Earth's version of office hours, flexible, but still hours. From the soft haze of morning to the clear cooling air of night, the sky breathes in and out, a slow, steady pulse written in vapour. It all begins before sunrise. In the darkness, the ground radiates heat away into space, cooling the air closest to it. This layer of chilled air is dense and stable, trapping moisture near the surface. A faint mist or fog may form, especially in valleys or near water as the air reaches its dew point. Above this calm layer, the atmosphere is quiet. No convection, no turbulence, just the soft drift of high clouds catching the first hints of dawn. If you look carefully, you can sometimes see cirrus glowing long before the sun itself rises, like the sky stretching before the day begins. As light touches the landscape, everything starts to change. The ground warms first, and with it, the air resting just above. Pockets of warmer air begin to rise, expanding as they climb, and the day's first thermals take shape. This is the birth of the boundary layer, the lowest part of the atmosphere where air interacts directly with the Earth's surface. In the early morning, this layer might be just a few hundred meters deep, but by midday it can grow several kilometers tall, carrying moisture, dust and heat upward. As the boundary layer grows, small cumulus clouds begin to form. They appear like shy newcomers, scattered across the sky in soft puffs. The timing depends on how quickly the ground heats. Dry land warms fast, while moist ground or water lags behind. Over open fields or sunlit plains, the first cumulus clouds often appear mid-morning, marking the top of invisible columns of rising air. Over lakes or oceans, the same process is slower and subtler. By early afternoon, the atmosphere is fully awake, the surface heat peaks, the updrafts strengthen, and the clouds grow taller and puffier. This is why afternoons so often look cloudier over land. The air near the ground is at its warmest and thermals are lifting moisture high into the sky. Each puff of air rises, cools and condenses into cloud, building layer upon layer. The result is a sky full of fair weather cumulus, bright, buoyant and constantly reshaping themselves. Not all of these clouds remain friendly, of course. On especially warm or humid days, those rising towers can evolve into cumulus congestus, or even cumulonimbus, the thunderclouds of late afternoon. But even without drama, the day's rhythm is unmistakable. The sun heats, the air lifts, clouds blossom, and the atmosphere hums with energy. Pilots and gliders know this dance intimately. They rely on the timing of thermals, riding invisible elevators of warm air through a sky thick with motion. Meanwhile, over the oceans, the pattern is reversed. Water heats and cools more slowly than land, so the sea surface stays relatively stable throughout the day. Instead of a deep, bubbling boundary layer, the marine atmosphere remains capped by cool, moist air beneath a temperature inversion. During the day, the sunlight can break up some of the marine stratocumulus decks, creating patchy skies and glimpses of blue. But when night returns and the sea surface cools slightly, those same clouds reform, knitting themselves back into the soft, endless quilts that stretch over vast ocean basins. Where land clouds prefer the afternoons, ocean clouds favour the night. As afternoon slips toward evening, the energy begins to drain from the system. The sun sinks lower, the ground starts to lose heat, and the updrafts weaken. Without the rising thermals to feed them, cumulus clouds lose their vigour, their edges blur, their bases rise, and they start to evaporate. By dusk, the once busy sky quiets again, the clouds thinning into veils of pastel pink and gold. The boundary layer contracts as cooler air settles, pressing the day's warmth upward and out. The process is gradual, but you can feel it in the stillness. The wind easing, the air smoothing, the light softening. After sunset, the atmosphere doesn't simply stop, it reorganizes. A thin layer of cool, stable air spreads over the surface, cutting off the convective currents that fed the day's clouds. Above this calm layer, the winds may accelerate, forming what meteorologists call a nocturnal jet, a fast, narrow ribbon of air that races through the lower atmosphere. You can't see it, but its presence can sometimes be felt as a faint breeze stirring the trees long after the ground below has gone still. It's the sky's version of after-hours maintenance, redistributing momentum while most of the world sleeps. By nightfall, the only clouds left are the high, icy ones, cirrus drifting in the upper winds, or thin sheets of stratus that form as air near the ground cools and moisture condenses. These low clouds can bring fog to river valleys or soft mist to meadows, carrying the day's warmth back to earth in droplets of dew. If the night is clear, the temperature can drop quickly, and the stars grow sharper. If it's cloudy, the clouds trap the day's heat, keeping the night mild. Either way, the atmosphere continues its quiet cycle, linking day and night through the invisible work of moisture and motion. This daily breathing of the sky, rising, mixing and settling, has been happening for billions of years. It shapes weather patterns, drives local winds, and influences everything from air quality to rainfall. It's easy to overlook, yet every sunrise begins the same slow rhythm again. Cool air at dawn, clouds swelling at noon, and calm clarity at dusk. If you were to watch a time-lapse of the sky over a single day, you'd see it like a living thing. The pale morning haze lifting into gentle heaps, the bright afternoon full of motion and light, the purple dusk thinning to stars. It's a reminder that the sky isn't a static dome but a breathing dynamic system, one that keeps time with the turning of the earth. So when you look up tomorrow, take a moment to notice the pattern. The day's first light revealing the faintest clouds, the sun's warmth giving them form, and the evening quiet returning them to vapour. The sky keeps its own schedule, as reliable as a heartbeat, written in air and sunlight. And though clouds may seem whimsical, they are creatures of habit, working long hours but always finishing their shift just in time for the stars. High above the spinning earth, invisible rivers of air shape the weather below. These streams are vast, fast, and astonishingly organised. Nature's conveyor belts, no ticket required. They sweep moisture, heat, and energy across entire continents, painting the sky with long bands of cloud that stretch for hundreds or even thousands of kilometres. When you see a smooth veil of cirrus or a grey sheet that slowly thickens into rain, you're watching the atmosphere's grand choreography in motion. At the heart of this rhythm are fronts, the meeting places of different air masses. A warm front forms when a body of mild, humid air moves toward a region of cooler, heavier air. Unable to push the denser air aside, the warm air slides up and over it, spreading out in a slow, graceful ascent. As it climbs, it cools and condenses, forming clouds in tidy layers. The first sign is usually high, delicate cirrostratus, thin enough to let sunlight through but thick enough to give the sun or moon a halo. Hours later, those clouds thicken into altostratus, soft and grey, until the sky becomes a solid overcast of nimbostratus. Then the rain begins, steady, soaking, and rarely hurried. It's the patient sort of rain that waters entire countrysides, not the tempestuous kind that shouts and storms. A cold front, on the other hand, is a more assertive character. Here, cold, dense air pushes underneath the warm air like a slow-moving bulldozer, forcing it sharply upward. The warm air rises fast, cools quickly, and condenses explosively. This is the kind of lift that builds towering cumulonimbus clouds, those dramatic skyscrapers of vapour that flash and rumble their arrival. Cold fronts bring change in a hurry. Gusty winds, sudden rain, perhaps a roll of thunder, and then a rush of cool, clear air in their wake. From above, the patterns are astonishingly elegant. A mid-latitude weather system, viewed from a satellite, looks like a vast spiral brushed across the planet. The warm front stretches out like a long arm of layered cloud, while the cold front curves behind it in a sharper sweep. Between them lies the warm sector, a wedge of moist air feeding the entire system. Within that wedge, countless currents rise and fall, balancing heat and moisture as they travel. The clouds don't just mark where weather happens, they are the weather made visible. Ahead of a warm front, the sky changes by degrees. Hours before any raindrop falls, the upper air has already begun to lift and cool. High ice clouds spread out like silk threads, followed by veils of cirrostratus that blur the blue. Next comes a lowering canopy of altostratus, diffusing the sunlight into a silver glow. By the time the first drops reach the ground, the process has been unfolding quietly for hundreds of kilometres, a reminder that weather is rarely sudden. It only seems that way from the ground. These fronts and cloud bands don't move alone. They're guided and powered by the jet streams, fast-moving ribbons of air that race through the upper troposphere at speeds over 200 kilometers per hour. Jet streams form where temperature contrasts are strongest, usually between polar and tropical air masses. They snake around the globe, helping to steer storms and set the pace of weather systems. When the jet accelerates or bends, it creates areas of rising and sinking air below. Where the flow diverges aloft, air must rise from beneath to fill the space, and that rising motion forms clouds. Meteorologists call these regions jet streaks, zones of particularly strong wind within the jet stream. At the entrance and exit of a jet streak, the air accelerates or decelerates, creating subtle upward or downward motions. These invisible patterns carve long sweeping cloud bands that follow the jet's path, often visible from space as elegant ribbons across the hemisphere. It's another reminder that even the smoothest looking layers of cloud are shaped by immense unseen forces flowing miles above. When a jet stream strengthens, it can feed an entire storm, drawing warm, moist air upward like a pump. When it weakens, the sky can clear almost instantly. The interplay between these upper-level winds and the surface fronts gives mid-latitude weather its variety. Days of calm grey drizzle, sudden bursts of rain, and clear nights that follow as if nothing happened. If you've ever watched a change in the weather approach, you've seen this process play out in miniature. The day begins with faint streaks of cirrus high in the west, then the sky whitens, then greys, until sunlight fades into a soft, featureless glow. Finally, hours later, the rain begins, gentle, deliberate, inevitable. The clouds you see overhead are only the visible fringe of a system stretching thousands of kilometers across, moving in perfect synchrony with the planet's larger winds. Even at night, the atmosphere continues its work. The jet stream hums quietly above, carrying waves of moisture from ocean to continent, from tropic to pole. Meteorologists sometimes call these flows atmospheric rivers, narrow corridors of concentrated water vapor that can deliver immense rainfall when they meet mountains or slow-moving fronts. From space, they look like shimmering bands of vapor crossing the oceans, each one capable of filling rivers and lakes on the other side of the world. It's humbling to realize that the rain falling softly on your window may have begun as vapor thousands of kilometers away, gathered and carried across oceans by these silent highways in the sky. The clouds we see are merely signposts tracing the pathways of an atmosphere always in motion, so when you look up and notice long, even layers stretching across the horizon, remember what you're seeing. They are the surface of invisible waves, the gentle crests of rivers of air flowing far above. They move heat, moisture, and momentum from one side of the world to the other, shaping the climate of every place they pass. The next time a sheet of rain sweeps across the land, picture it as part of a vast planetary current, nature's conveyor belts in motion, endlessly circling, endlessly renewing. When most of the world has gone dark and the sun has long dipped below the horizon, a strange silvery light sometimes lingers high in the sky. It shimmers, faint yet unmistakable, like threads of electricity woven into the deep blue of twilight. These are noctilucent clouds, the highest clouds on Earth, drifting at the edge of space where the atmosphere fades into nothing. They are clouds that prefer the night shift. While ordinary clouds live in the lower atmosphere, the noctilucent, or night-shining, clouds form in the mesosphere, around 80 kilometers above the ground. That's roughly 10 times higher than the typical cumulus you see on a summer day, and nearly twice as high as even the loftiest cirrus. Up there, the air is so thin that it would make a good vacuum by earthly standards, and so cold that temperatures drop to around minus 130 degrees Celsius. Under such extreme conditions, water vapor alone isn't enough to make a cloud. It needs help from the cosmos. Every year, tens of tons of micrometeorites drift into Earth's atmosphere. Most burn up unseen, but they leave behind trails of fine dust, tiny mineral particles suspended high above the world. These specks become the seeds of noctilucent clouds. When the upper atmosphere cools during summer, the rare traces of water vapor up there freeze onto the dust, forming microscopic ice crystals. Each crystal is a sliver of ice clinging to a piece of stardust. It's one of those beautiful ironies of nature, clouds made from both water and the remains of meteors, born of earth and sky at once. They form most often in summer, not winter, which surprises many people. The reason lies in the strange circulation of the upper atmosphere. During summer, strong upward winds near the poles carry air into the mesosphere. As the air rises, it expands and cools, much like the process that makes cumulus clouds down below. This cooling is so effective that the mesosphere over the poles becomes the coldest region of the atmosphere. Even in sunlight, it's cold enough for ice to form. Noctilucent clouds owe their eerie glow to geometry. After sunset, when the lower atmosphere is already in shadow, the sun still illuminates the mesosphere from below the horizon. The icy particles of the clouds scatter this sunlight toward the observer, making them visible against the darkening sky. It's a delicate trick of timing. Too early, and the glare of daylight hides them. Too late, and the sun drops too far below the horizon to reach them. The best viewing time is usually between 1 and 2 hours after sunset or before sunrise, when the world below is dark but the edge of space is still catching the sun's rays. From the ground they appear as fine glowing filaments, silver, blue, and occasionally tinged with gold or violet. They ripple and weave like silk curtains caught in an invisible breeze. Sometimes they form delicate meshes or wave patterns, shaped by atmospheric tides and gravity waves travelling upward from below. To see them is to witness the sky itself shimmering. They seem alive, and in a way they are. Each flicker and fold reveals the unseen movements of the atmosphere tens of kilometres above. Despite their beauty, noctilucent clouds are a recent discovery. The first recorded sightings came in the late 19th century, shortly after the massive eruption of Krakatoa in 1883. People across Europe began reporting strange luminous clouds at twilight, glowing far above the normal weather layer. At first, scientists thought they were caused by volcanic dust, but the phenomenon persisted long after the ash had settled. Eventually, it became clear that these clouds belonged to an entirely different realm, too high to touch by balloon or airplane. Today, satellites and high-altitude instruments have revealed much about their nature, but they also remain a mystery. They're extremely sensitive to changes in temperature, humidity, and the amount of water vapor at their altitude. Even a small shift in the chemistry of the upper atmosphere can affect their brightness and frequency. Over the last few decades, noctilucent clouds have become more common and visible farther south than ever before. Some scientists suspect this is linked to rising greenhouse gases. Paradoxically, while the lower atmosphere warms, the mesosphere cools, a side effect of increased carbon dioxide radiating heat away into space. Cooler upper air means more ice and more noctilucent clouds. In that sense, these shimmering veils may be a subtle signal of a changing planet. They are the highest clouds, but also among the most delicate, forming only when conditions are just right. Even a trace more or less of water vapour can make the difference between a glowing display and an empty sky. Their presence reminds us that Earth systems are deeply connected from top to bottom. What happens on the ground can echo all the way to the edge of space. To spot them, you need patience and a bit of luck. Find a clear horizon to the north if you live in the northern hemisphere, or to the south if you're in the southern hemisphere. Wait for a deep twilight in summer, when the sun has set but the sky hasn't gone fully dark. If you see faint silvery streaks glowing against the dark blue, shifting slowly as if stirred by a distant wind, you've found them. They're ghosts of ice and stardust, lingering where day and night meet. Seen from space, noctilucent clouds look like shimmering blue webs wrapped around the poles, tracing the limits of sunlight as the Earth rotates. Astronauts on the International Space Station often describe them as the most hauntingly beautiful sight in orbit. Fragile glowing bands that drift along the edge of the world. From up there, they are neither fully part of Earth nor entirely part of space, suspended in the boundary between both. There's something humbling about these clouds. They are fleeting, fragile, and yet profoundly ancient in spirit. Their materials, water, air, and cosmic dust, are the same ones that shape the early solar system. When they appear, they remind us that even in the thinnest reaches of our atmosphere, where air molecules barely brush against one another, beauty finds a way. So the next time you find yourself under a clear summer night, look toward the dim horizon after the sun has gone. You might see them faintly glowing there, electric silver threads above the midnight world rippling silently through the upper air. They are clouds that prefer the night shift, painting reminders across the heavens that even the edge of space isn't beyond the touch of light. On some days the sky wears handwriting. Long white lines stretch from horizon to horizon, drawn by aircraft passing far above. They linger, twist, and sometimes spread into wide feathered veils that look almost natural, except that they weren't there an hour ago. These are contrails, condensation trails, and though they vanish silently into the blue, they mark one of the most visible ways humans have joined the planet's cloud makers. They're pencils in the sky, gradually smudged by the wind. Contrails form in the same way that any cloud does, by condensation, but with a few extra steps courtesy of jet engines. At cruising altitude, roughly 10 to 12 kilometers high, the air is cold, often below -40 degrees Celsius, and very dry. When a jet engine burns fuel, it releases carbon dioxide, water vapor, and a mix of tiny soot and sulfate particles. That water vapor, though small in amount, can momentarily saturate the surrounding air. As it mixes with the cold, ambient atmosphere, the moisture freezes almost instantly around those microscopic particles, forming countless tiny ice crystals. The result is a slender, brilliant white line. A man-made cirrus cloud born from fire and frost. Not every plane leaves a contrail. The air has to be cold and moist enough for the exhaust to reach saturation before the crystals sublimate away. When the upper atmosphere is too dry, the trail evaporates in seconds. When it's humid, the contrail can persist for hours, widening and spreading as wind shear stretches it into thin, fibrous sheets. Within minutes, a crisp line becomes a soft ribbon. Within an hour, it may be indistinguishable from natural cirrus. In busy flight corridors, these trails can merge into veils that subtly brighten the daytime sky or blur the sunset into milky hues. Each contrail is a perfect little chemistry and physics lesson. The soot and aerosols from combustion serve as nuclei for the ice crystals, much like dust or salt particles in natural clouds. But here the process is amplified. Each engine emits billions of potential seeds every second, producing clouds that wouldn't otherwise exist. Over the course of a single day, global air traffic can create millions of square kilometers of additional high cloud cover. Most of it is thin, but even thin clouds can affect how sunlight and heat move through the atmosphere. Contrails and the cirrus layers they spread into have a mixed effect on climate. During the day, they reflect some sunlight back to space, producing a small cooling effect. At night, though, they trap infrared radiation from the surface, preventing heat from escaping. Because flights often cluster in the morning and evening hours, when the sun's angle is low, the warming effect tends to outweigh the cooling one. It's subtle, nothing dramatic on any single day, but persistent enough to show up in global energy balance measurements. When air travel briefly paused in the early 21st century, scientists noticed measurable changes in the temperature range between day and night, confirming that even our skywriting has consequences. While contrails are the high-altitude expression of human influence, the oceans have their own version, ship tracks. These are long, narrow streaks of cloud that form in the wake of large vessels. You can't usually see them from the deck, but from space they're unmistakable. Bright silvery lines etched across marine stratocumulus decks. Their physics is surprisingly elegant. As ships burn fuel, their exhaust releases tiny particles into the moist marine air. These particles act as additional condensation nuclei, allowing many more cloud droplets to form than would naturally occur. Here's where the balance changes. When more droplets compete for the same amount of water, each one grows smaller. Smaller droplets scatter light more efficiently, making the cloud appear brighter and more reflective. In other words, ship tracks create artificial clouds that cool the planet slightly by bouncing more sunlight back into space. This phenomenon, called the Toomey effect, shows how even subtle changes in particle number can alter a cloud's appearance and behaviour. However, there's a trade-off. Brighter clouds may reflect sunlight, but they also alter how the cloud evolves. Smaller droplets are less likely to collide and merge into raindrops, meaning the cloud lasts longer. Longer-lived clouds can trap more heat at night, just like contrails do. Whether the net result is cooling or warming depends on time, location and season. In marine regions where the sun is strong, the reflective effect dominates. In darker or nighttime conditions, the warming influence can take over. Even something as simple as a ship's exhaust can tip the balance one way or the other. In recent years, scientists have studied ship tracks not just as curiosities, but as natural experiments, tiny laboratories drifting across the ocean sky. They offer insight into how pollution affects cloud formation and reflectivity, helping refine climate models. Their visibility also underscores how sensitive clouds are to human activity. The air doesn't care whether its nuclei come from sea salt, dust or diesel. It simply responds to the ingredients it's given. There's something poetic about this, even amid its implications. Every contrail and ship track is a fleeting footprint, a brief trace of our presence that the atmosphere soon erases. The wind smooths them out, the ice crystals sublimate, and within hours the sky looks untouched. Yet collectively, those short-lived clouds can nudge the planet's thermostat ever so slightly. It's a reminder that even the gentlest acts, travel, motion, connection, leave marks on the natural systems that sustain us. If you've ever lain back and watched planes cross high overhead, you've probably noticed how quickly their trails change. The lines spread, twist and weave together, turning into faint silky veils that seem to drift aimlessly. But if you trace them far enough, you're following a chain of cause and effect stretching from the engines to the edge of the atmosphere. Every faint shimmer of ice began as invisible water vapor and heat, frozen instantly into crystal form, then carried on the wind to become part of the weather itself. From the surface, these man-made clouds can make sunsets more luminous, scattering light into peach and rose tones that linger long after the sun is gone. From space, they resemble threads of silver sewing together the continents and oceans. They are a product of movement, of connection, our species' restless urge to go farther and faster, and so the sky, once purely shaped by nature, now bears our signature too. The next time you see a straight white line stretching overhead, think of it as an instant cloud, a mixture of physics, flight, and fleeting beauty. It will fade soon enough, blending into the natural sky it imitates. For a brief while, though, the atmosphere itself becomes a living notebook, filled with pages written in vapour and erased by the wind. If the Earth had a thermostat, it would be made of clouds. They are the world's most complicated thermostat. No batteries required. Without them, the planet would be a sunburned desert. With too many, it would be an icy mirror. Every moment, clouds juggle sunlight and heat, deciding how much energy enters and how much escapes. They cool and warm the world at once, reflecting some of the sun's rays back to space, while trapping some of Earth's warmth beneath their soft blankets. The balance they strike keeps our planet livable and incredibly delicate. To understand their role, imagine Earth sitting on a cosmic scale. On one side is sunlight, the shortwave radiation pouring in from the sun. On the other is the long-wave infrared radiation that Earth emits back to space. Clouds weigh in on both sides, sometimes tipping the balance one way, sometimes the other. It all depends on their altitude, thickness, and brightness. Low clouds, such as stratus or marine stratocumulus, are Earth's reflectors. They are thick, bright, and often widespread, covering huge portions of the ocean. Their tops gleam white under sunlight, bouncing a large share of that light back into space before it can warm the surface. This reflective power, known as albedo, gives them a strong cooling effect. Even a small increase in their coverage can lower regional temperatures by a degree or two. On a global scale, they're like an enormous parasol shading the planet. High clouds, such as cirrus, play a very different game. They're thin and wispy, allowing most sunlight to pass through, but they excel at trapping infrared radiation rising from the surface. Because they sit 10 kilometers or more above the ground, in much colder air, they absorb heat and re-emit it downward, slowing the planet's nighttime cooling. These clouds act less like parasols and more like delicate thermal blankets. The result is warming rather than cooling. The key to the planet's temperature lies in the tug-of-war between these two kinds of clouds. Low clouds mostly cool, high clouds mostly warm. The global balance between them, how much sky each kind occupies, and where, is a crucial part of Earth's climate system. Change the ratio just a little, and you change the planet's energy budget. It's one of the reasons climate models devote so much effort to understanding cloud formation. They are both the largest source of uncertainty and the most important variable in predicting future climate. The interplay between shortwave reflection and long-wave trapping is beautifully subtle. When sunlight hits a low cloud deck over the ocean, up to 70% of it can be reflected back into space. But when that same sunlight passes through high cirrus clouds, almost all of it reaches the surface. Later, as Earth emits infrared radiation, the cirrus absorbs much of it, keeping the warmth from escaping. The two processes, reflection and retention, happen at the same time, every second of every day, all over the world. The net effect of clouds on climate depends on which side wins more often. At present, clouds cool the Earth overall. On average, they reflect more sunlight than they trap heat, reducing the global temperature by several degrees compared to a cloudless planet. But that doesn't mean the system is stable. Warming air holds more moisture, and changing wind patterns shift where clouds form and how long they last. Even a small increase in high, thin clouds, or a slight decrease in low, thick ones could flip the balance, amplifying global warming. That's why scientists say clouds are the great uncertainty in climate projections. Their future behaviour could either soften or sharpen the planet's fever. Some of the most fascinating cloud climate feedbacks happen where sunlight and water meet. Over the tropical oceans, low marine stratocumulus clouds act as massive mirrors, reflecting sunlight that would otherwise heat the sea. If warming reduces these clouds, more sunlight gets absorbed, warming the water further and thinning the clouds even more, a runaway loop of cause and effect. Conversely, in polar regions as sea ice retreats, more moisture rises into the air, creating extra clouds that might reflect sunlight and slow the melt. The atmosphere is a web of balancing acts, each one delicate, each one capable of shifting the planet's trajectory with the faintest nudge. What makes clouds especially tricky to study is their variability. A single type can change its character in minutes. Add a bit more moisture or lift, and a flat stratus becomes a field of cumulus. Introduce dust or pollution, and droplet numbers change, altering brightness and longevity. Even the shape of a coastline or the texture of the land can steer air currents enough to change local cloud cover. Multiply those micro-level details across an entire planet, and the complexity becomes staggering. Satellites help us see the patterns more clearly. They track the Earth's radiative balance, the difference between energy in and energy out, allowing scientists to map where clouds are cooling or warming most effectively. Over bright deserts, clouds have a weaker cooling effect because the surface is already reflective. Over dark oceans or forests, they matter enormously. Meanwhile, in the tropics, high cirrus layers play a double role, reflecting sunlight during the day but trapping heat at night, like translucent quilts that never stop working. The numbers are extraordinary. At any given moment, roughly 2/3 of Earth's surface is covered by cloud. These clouds reflect nearly 1/5 of incoming solar radiation. They also absorb about 1/4 of the infrared energy leaving the planet. That balance, so even, so precise, keeps the climate within a narrow band of habitability. Shift it slightly, and everything else adjusts. Winds, rainfall, temperature, even the chemistry of the oceans. When you look up at the sky, it's easy to forget how finely tuned it is. The clouds drifting overhead aren't just weather, they're regulators of the planet's heartbeat. They manage light and warmth with the precision of a vast natural thermostat. Yet unlike the devices on our walls, this one has no dial, no simple switch to adjust. Its settings are written in the movements of air and water, in the balance between reflection and radiation. Picture it like a scale tipping gently between brightness and warmth. Each new cloud adds a weight to one side, then another. A patch of low stratus brightens the day but cools the night. A veil of cirrus does the opposite, dimming little but trapping more heat after sunset. The global average of these countless exchanges is what determines whether our world warms, cools, or holds steady. For all our scientific sophistication, clouds remain humbling. They're ordinary enough to fill the afternoon sky, yet complex enough to confound supercomputers. They remind us that the planet's stability depends on small, fleeting things. Droplets no wider than a hair, ice crystals drifting miles above, and air currents we can't even see. So the next time you look up at a sky full of clouds, remember you're looking at the planet's control system in action. Those drifting shapes are not just decorations of weather, but the guardians of balance, forever managing the trade between light and heat. They are Earth's thermostat, quiet, beautiful, and endlessly precise. For as long as people have watched the weather, they've wondered whether it could be persuaded to change its mind. The sky seems so expressive, so full of movement, that the temptation to give it a little nudge has always been there. The idea is simple in spirit and impossibly complex in practice. If clouds can cool or warm the planet, could we learn to adjust them just a little? It's one of those concepts that sounds easy to talk about but hard to edit. The notion of cloud seeding began in the mid-20th century, when scientists first learned that certain particles could encourage water droplets or ice crystals to form. The idea was to help coax rain from reluctant clouds. In the late 1940s, researchers in the United States discovered that silver iodide crystals, with their hexagonal structure, mimicked natural ice and could trigger freezing in supercooled clouds. Planes began releasing tiny amounts of it into cold clouds to see whether precipitation would follow. Sometimes it worked, sometimes it didn't. The results were as unpredictable as the weather itself. The principle behind it, however, is sound. Clouds are constantly deciding whether to rain or not, based on the number and size of droplets inside them. Add a few extra particles, and you might change the balance. In cold clouds, ice nuclei encourage water vapor to freeze, leading to snowflakes or raindrops as the crystals grow and fall. In warm clouds, hygroscopic particles like salt can help droplets merge faster, accelerating rainfall. The challenge lies in scale. A small aircraft or a few rockets can influence a single storm, perhaps a valley or a mountain range, but the atmosphere is vast and interconnected. Local adjustments rarely stay local for long. Over the decades, dozens of countries have experimented with cloud seeding, often hoping to increase rainfall in dry regions or reduce hail in vulnerable agricultural areas. Some projects reported success, others saw no clear change. The difficulty isn't just making it happen, it's proving that it happened because of us. The natural variability of weather makes cause and effect slippery to measure. For every cloud that rains after seeding, there's another that would have done so anyway. Monitoring and verification remain as challenging as the process itself. In recent years, as the conversation about climate change has grown more urgent, attention has shifted to the potential for using clouds not just to make rain, but to manage sunlight. This is where marine cloud brightening comes in, a proposal to make the planet a little shinier. The concept is based on a natural process. When ocean spray throws salt particles into the air, they act as cloud condensation nuclei, allowing clouds to form with many small droplets. These smaller droplets scatter sunlight more efficiently, making the clouds appear brighter and reflecting more energy back into space. In theory, enhancing this process slightly could cool the Earth's surface in targeted regions. To test the idea, scientists have designed sprayers that could release fine mists of seawater into the air, mimicking natural sea spray but on demand. The hope is to increase the brightness of marine stratocumulus clouds over parts of the ocean where sunlight is strong and clouds are abundant. These low, thick clouds already have a large cooling effect. Brightening them by even a few percent could, in principle, offset some of the warming caused by greenhouse gases. The physics is relatively straightforward, but the scale of uncertainty is vast. Because clouds are sensitive systems, small changes can ripple outward in unexpected ways. A brighter cloud might cool the surface below, altering local wind patterns or humidity. Those shifts could, in turn, change rainfall hundreds of kilometers away. The feedback loops are intricate, and our models, while improving, are still approximations of an atmosphere far more complex than any equation. What looks stable in a simulation may behave differently in reality. There's also the question of permanence. Marine cloud brightening, unlike cutting emissions, doesn't remove carbon dioxide. It only masks some of its warming effect. If such efforts were ever stopped, the cooling would vanish quickly and the climate could rebound with sudden heat. That raises ethical questions about commitment and responsibility. Once begun, who decides when to stop? And how do you balance regional benefits against potential global side effects? Scientists working on these ideas tend to be cautious, not visionary heroes trying to rewrite the weather, but careful observers in quiet laboratories and coastal test sites. They speak in uncertainties, probabilities, and ranges. They keep notebooks filled with measurements of droplet sizes, wind speeds, and sunlight intensity. Evidence gathered patiently rather than promises made loudly. Their work isn't about controlling nature so much as understanding how fragile its balance really is. Even the practicalities are daunting. To noticeably brighten a patch of marine cloud, a fleet of ships or coastal stations would need to spray seawater continuously over large areas, maintaining droplet concentrations within a narrow range. The atmosphere, however, is not a still canvas. Winds shift, air mixes, clouds evolve. What begins as a bright patch might drift, dissipate, or merge with others. Measuring success would require satellite monitoring, global coordination, and years of data. And yet, these studies matter deeply. Whether or not marine cloud brightening or seeding ever becomes a viable tool, exploring them teaches us more about how the atmosphere works. Every field experiment refines our understanding of droplet physics, aerosol behavior and radiative balance. Sometimes the value lies not in the outcome, but in the act of asking the question carefully. Ethically, the conversation touches on something larger than technology. It's about trust. The climate belongs to everyone, and clouds don't respect borders. Any deliberate modification, even with the best intentions, affects a shared sky. Many researchers argue that before anyone attempts such interventions, there must be transparent international dialogue and strict oversight. It's one thing to seed a small rainstorm. It's another to adjust the reflectivity of a region's atmosphere. For now, these projects remain mostly theoretical or small-scale, their ambitions tempered by humility. The sky has been shaping itself for billions of years, guided by sunlight, gravity, and chemistry. Our understanding of it is still young. To edit the weather is to step into a system of extraordinary sensitivity, one that remembers every input, even those we didn't mean to make. In the end, cloud seeding and marine brightening may never become mainstream tools, or perhaps, in a future of dire necessity, they'll be used as temporary measures, carefully monitored and quickly withdrawn. Either way, their study reminds us of the atmosphere's complexity and our own responsibility toward it. The clouds, for all their gentleness, hold enormous power. So while the idea of brightening the sky might sound bold, the truth is quieter. It's the sound of a pen scratching in a researcher's notebook, of a cautious mind weighing possibilities against consequences. The work is slow, the tone measured, the intent respectful. Because if the atmosphere is the world's most intricate system, then any attempt to alter it must begin not with confidence, but with care. To truly understand clouds, you have to look at them from every angle, above, below, and even through. For most of human history, we saw only the view from the ground, gazing up at the sky like an ever-changing painting. But now, fleets of satellites and networks of radars give us another perspective entirely. They let us see the atmosphere as it really is, layered, dynamic, and alive. You might call it X-ray vision for the sky, minus the capes. Every day, dozens of satellites orbit Earth, quietly taking the planet's pulse. Some drift above the equator, fixed over the same patch of the world, while others circle from pole to pole, scanning the entire globe as Earth spins beneath them. Together they form an unbroken chain of watchers, mapping clouds, moisture, temperature, and motion. Their eyes are not like ours. They see in wavelengths invisible to human sight, revealing details hidden within brightness and shadow. The simplest way to observe clouds from space is with visible light. In these images, clouds appear white because they scatter sunlight in all directions, while land and ocean absorb most of it. This is the same light you see from the ground, only from a grander vantage point. But visible light has one weakness: it can't see in darkness. When the sun sets, the clouds vanish from these channels, leaving only blackness. To follow the atmosphere through the night, satellites need other senses. That's where infrared radiation comes in. Everything with a temperature emits infrared light, including clouds. By detecting this invisible glow, satellites can measure cloud top temperatures, which reveal their heights. Colder clouds are higher, warmer ones are lower. On night-side Earth, the planet itself radiates faint thermal energy, painting a ghostly map of heat and cold. High thunderstorms stand out as icy white towers against the warmer ground below. From this thermal perspective, you can watch the breathing of the planet, day turning to night, continents cooling, storms flaring and fading. Some satellites look at even more specific wavelengths, tuned to the spectral fingerprints of water vapor. These channels can detect moisture in the clear air between clouds, allowing scientists to see the hidden rivers of humidity that feed storms. They show how plumes of moisture travel from oceans to land, curving around pressure systems like invisible currents. Together, visible, infrared, and water vapor channels create a complete portrait. The bright and the dark, the seen and the unseen, all stitched together in light. While these instruments observe passively, simply collecting the radiation that Earth emits or reflects, others take a more active approach. Radar and lidar systems send out pulses and listen for their echoes. Weather radar, for instance, transmits radio waves that bounce off raindrops, snowflakes, or hailstones. The strength of the returning signal, called reflectivity, tells us how dense the precipitation is, while the time delay reveals how far away it is. By measuring the frequency shift of the reflected waves, meteorologists can even determine whether rain is moving toward or away from the radar, mapping wind patterns within storms. In space, specialized radars work the same way on a global scale. The CloudSat satellite, for example, carries a cloud profiling radar that can slice vertically through the atmosphere, showing the structure of clouds from top to bottom. Its companion mission, CAL-PSO, adds a lidar, essentially radar that uses light instead of radio waves, to detect fine layers of aerosol and thin cirrus clouds that radar might miss. Together, they reveal the atmosphere's texture in exquisite detail: stacked decks of cloud, plumes of dust, ribbons of smoke, and the delicate curtains of ice drifting at the edge of space. By comparing data from different wavelengths, scientists can infer properties that no single instrument could reveal. Visible light shows the outlines of clouds, infrared shows their temperature, microwave sensors penetrate through thick layers to measure the water and ice inside. Radar tracks movement, lidar maps thin haze, and combined they create a three-dimensional view of an ever-moving world. It's like listening to a symphony of signals, each instrument contributing its own tone to the composition of weather. All this information flows into what might be called the cloud archive, a growing digital memory of Earth's sky. For decades, satellites have been recording cloud cover, brightness, altitude, and motion. This long record lets scientists trace how cloud patterns shift with the climate. They can see, for example, how tropical storm clouds have changed in height, or how the subtropical cloud belts have inched poleward as the planet warms. What once required years of ground observations can now be seen unfolding in real time from orbit. Ground-based instruments join in the effort too. Networks of weather radars sweep across continents, watching storms evolve minute by minute. Lidar stations measure aerosol layers and thin cirrus, while ceilometers, small lasers pointed straight upward, record cloud base heights through day and night. When stitched together with satellite data, these observations form a bridge between what we see from above and what we experience below. The result is an atmosphere no longer guessed at, but mapped, pixel by pixel, from sea level to the edge of space. Beyond their scientific precision, these technologies offer something quietly poetic. From orbit, the Earth's night side glows faintly in infrared, its warm continents outlined by invisible light. Bands of cloud drift across like silver brush strokes, their tops illuminated by the lingering heat of day. A hurricane looks like a living spiral, its cold heart ringed by warmth. Even the thin lines of contrails show up, tracing the geometry of flight across the upper sky. It's a perspective that feels both scientific and deeply human, seeing the weather not just as experience, but as pattern and pulse. Yet for all the sophistication of our tools, the atmosphere still guards its mysteries. Satellites can measure brightness to astonishing precision, but they can't always tell exactly how droplets form, or why one cloud rains while another doesn't. The sensors give us the outlines. The atmosphere fills in the details. Each new generation of instruments improves our view, but the sky always seems to stay one layer ahead, teasing with complexity. Even so, the achievement is remarkable. Humanity has learned to look at its own weather from the outside, to see the world as both system and story. Every orbiting satellite, every ground radar spinning in the rain is part of that shared act of curiosity. They don't just forecast the next storm, they preserve the memory of all the ones that came before, creating a vast living library written in waves and echoes. So the next time you glance at a weather map, imagine what lies behind those colourful swirls and cloud bands. Somewhere above, a satellite is tracing the warmth of clouds on the night side of Earth, while radar dishes hum softly in the rain, adding their notes to the great recording. Together they form the planet's eyes, patient, tireless, and quietly watching the breath of the sky. If you step outside on a quiet night and look up, the sky looks still. Yet every shape you've watched in these hours has been in motion, hidden breath moving through a planet that never truly rests. A cloud is the softest evidence of that breath. It begins with something so small it slips past notice. A few molecules of water finding a surface, a dust grain, a salt crystal, the faintest seed. A pocket of air rises, cools, and crosses an invisible threshold where the unseen becomes seen. From that moment on, a story unfolds, patient, precise, and endlessly renewed. We followed that story from the first shimmer of droplets to whole cities of vapour. We watched air climb sun-warmed fields and drift over mountains. We saw it gather itself into small fair-weather puffs, and then, on days ripe with energy, build towers that brush the boundary of space. Inside those towers, droplets collided and merged, ice formed and broke apart, and lightning found its path through crowded crystals. Then the same energy that raised the cloud released it again. Rain fell, air cooled, and the sky returned to calm like a deep breath let out. We learned the family names that help make sense of the sky's moods. Sheets that stretch from horizon to horizon, heaps that bloom and fade, wisps combed thin by high winds. We traced their homes by height, low decks that shade the oceans, middle layers that soften the sun, high ice that plays with moonlight. Each form decided by simple balances, how quickly the air cools with height, how much moisture it carries, how gently or forcefully it is lifted. The Latin may be old, but the meaning is immediate. Shape follows physics, and the physics is written in light and motion. Out at sea we drifted under the planet's great coolers, the marine stratocumulus quilts that reflect sunlight back to space. Their tops are stitched by gentle overturning, their edges maintained by the lightest drizzle, drops that fall and vanish before they reach the waves. They look placid from above, yet they manage the world's warmth with quiet authority, adjusting the day's brightness by the smallest of degrees. Over ridges and peaks we stood beneath lenticulars, smooth and steady, formed by standing waves in moving air, stationary sculptures carved by flow. They remind us that even when a cloud seems fixed, the air within is forever passing through. At night we walked under high cirrus, ice arranged into columns and plates so delicate that the moon can paint rings and pillars around itself. We looked for glories and halos and rainbows and found that colour in the sky is simply light learning the structure of water and ice. We stood in the fog and found the sky visiting the ground, a cloud at our doorstep that softened footsteps and blurred the ordinary into something tender. We watched a day unfold as the boundary layer woke. Puffs gathered through afternoon, then loosened and thinned toward dusk. We saw the wide conveyor belts of fronts and the quick fingers of jet streaks, cloud bands arriving like long veils that announced gentle rain hours in advance. We travelled higher still to the edge of night, where noctilucent clouds glow after sunset, thin lace of ice on meteoric dust, lit by a sun already hidden from us. They are reminders that Earth's atmosphere is layered far beyond weather, and that the highest pages of the sky are sensitive, responsive, and tied to changes below. We traced our own signatures too, lines from aircraft feathered into veils and joined the high ice. Over the oceans, ship tracks brightened patches of cloud by dividing the water among many more droplets. Some of these fingerprints reflected sunlight and cooled the surface below. Some trapped warmth after dark. The effects were small but measurable, a gentle nudge to the planet's balance that echoed the lesson repeated everywhere. In the sky, little things matter. We listened in on careful conversations about whether clouds could be adjusted on purpose. Could a patch of marine deck be brightened slightly by fine sea spray? Could cloud seeds nudge a hesitant sky toward rain? The answers so far arrive with humility, sometimes a little, and always with uncertainty. The atmosphere is a web, and each touch trembles far beyond the point of contact. If such ideas are ever used, they will require patience, shared consent, and the understanding that editing weather is not a cure, only a temporary shade drawn across a warming window. We also learned how to see more than the eye alone can see. Satellites watched in visible light by day and in thermal glow by night. Radars and lidars sent pulses and listened for echoes, and together they built a memory of clouds across decades. Those records show patterns shifting, bands inching, heights changing. The archive is a quiet promise. If we look carefully and long enough, the sky will tell us what it is becoming. What ties all of this together is a cycle so familiar we sometimes forget to notice it. Water evaporates from warm surfaces, travels invisibly, condenses into cloud, falls as rain or snow, and begins again. Each step is an exchange of heat, a trade between light and warmth, a small adjustment of the planet's scales. Clouds cool and warm, darken and brighten, shade and insulate, always searching for equilibrium while the world turns beneath them. In that sense, clouds are not just weather, they are the planet's breath made visible. When you see a flat base stretched across a summer sky, you're seeing the level where air first became saturated. When you watch an anvil spread, you're seeing the limit of a day's ambition. When the moon wears a halo, ice crystals are telling you how the upper air is arranged. When fog curls around a bridge, the ground is reminding the sky that they share the same air. Every calm night and rainy day belongs to this patient conversation. If you listen closely, the sky offers a kind of reassurance. It will be different tomorrow and yet familiar, because the rules that guide it are steady, kind, and endlessly creative. The same physics that makes a rainbow paints a storm. The same processes that shade the oceans knit sunlight back into warmth after dark. The same droplets that bead on a leaf have flown as mist, frozen as ice, and fallen as rain across mountains and cities and quiet fields. So, as the day closes and the world settles, let the clouds do what they have always done. Let them drift and gather and thin and return, moving energy and water with the grace of a long tide. Somewhere, a high veil is glowing in moonlight. Somewhere, a low deck is brightening an ocean by a fraction. Somewhere, a solitary puff is rising over warm ground, preparing to become the briefest of stories. And over all of it, the planet is breathing, slowly, evenly, in and out. If your eyes grow heavy, that's all right. The sky will keep its watch whether you see it or not. The droplets will continue their quiet work, the winds will draw their soft lines, and the balance between light and warmth will tilt and settle as it always has. Rest, and let the world's oldest cycle turn without you for a while. When you wake, look up. The clouds will be there, new and familiar, delicate and determined, ready to show once more how the earth keeps time